Righto, welcome back to Gauss-Jordan elimination. Okay, we've got here three linear equations. Linear because the powers of our variables are 1, okay, but it's in three unknowns. Okay, so we've got a system of simultaneous equations, but we have three unknowns. Okay, and when you've got three unknowns, you need three equations to solve it. Alright, so first step. Remember, we need to produce an augmented matrix. We need to have all our constant terms on the right hand side, and we can do that. Okay, so I've just got them written here, and you'll notice that all our constant terms are on the right hand side and all our terms with variables on the left hand side. Remember, the first step involved is to create an augmented matrix, and we're going to do that. We're going to ensure from the very beginning that if there are any rows that will have a 1 as their leading entry, then we'll put that as the first one. And you'll notice here, because our coefficients of x go first in the first column, let's scan through it. Notice this one here as a coefficient of 1, so we'll use this particular equation as our first row. So we've got 1, negative 1, 1 and 1. From there it doesn't matter. Okay, so we'll go 3, negative 1, 7 and 0, and then 4, negative 2, 8 and 1. Okay, so our first step has been accomplished, and we've got here our first row here as a leading entry of 1. Next step then is to ensure that in our first column all of these other entries have are 0. Alright, so we'll start with this first row here. So multiplying row 1 by negative 3 and adding it to row 2. We can do this we can sort of apply this in one step. And in the third row we multiply the first row by negative 1 by negative 4 and adding to row 3. So we've got negative 3 times row 1 plus row 2 to become row 2, and then negative 4 times row 1 plus row 3 to give row 3. Okay, so first of all, negative 3 times 1 is negative 3. Negative 3 times negative 1 is 3. We've got another negative 3 and another negative 3. We're going to add that to row 2, which is 3, negative 1, 7 and 0. When we add those, we get 0. 3 plus negative 1 is 2. Negative 3 plus 7 is 4. And negative 3. So this is our new row 2. Okay, so I'll just put it down here. We've still got 1, negative 1, 1 and 1. Now we have 0, 2, 4 and negative 3. I'll just leave the third row blank at the moment because we're going to do the same thing here. We're going to multiply the first row by, so we've got negative 4 times the elements on row 1, which is negative 4, positive 4, negative 4, negative 4. That needs to be added to row 3, which is 4, negative 2, 8 and 1. And so adding those, we get 0, 2, 4 and negative 3. And this then is our new row 3. 0, 2, 4, negative 3. Okay, next step has been done. Now, when we have a look, the next thing we want to do is multiply. We need to change our leading entry for row 2 to a 1. Okay, so the 2 here needs to be multiplied by 1 over 2. It's multiplicative inverse. Okay, so we go 1 over 2 times each element in row 2 2 to give us a new row 2. Alright, so in doing that we'll get 0, 1, 2 and negative 3 over 2. Alright, so 1, negative 1, 1 and 1, that's unchanged. 0, 1, 2 and negative 3 over 2. And then we've still got 0, 2, 4 and negative 3. So this is our leading entry in row 2 is 1. The next thing we need to do is ensure that every element in that column is a 0. So you'll notice that with our first row here and this element, to change that to a 0, we don't actually have to multiply our 1 here by anything, because what we can do is just add 1 to negative 1 to give 0. So we can just go row 2 plus row 1 to give us our new row 1. On the other hand, our third row we need to multiply by, or at least we need to multiply our row 2 by negative 2 and then add it to row 3. So we're going to go negative 2 times row 2 plus row 3 to give us our new row 3. Alright, so in doing that, let's do each one. Our row, well, our first one, because we don't need to do any multiplying and adding, we can simply add. 0 plus 1 gives 1, so that remains unchanged, which is what we want. 1 plus negative 1 is 0, 2 plus 1 is 3, and then negative 3 over 2 plus 1, or negative 1.5 plus 1 is going to be negative 1/2. Our second row remains the same, 0, 1, 2 and negative 3 over 2, and our third row we work it out this way. We're multiplying our second row by negative 2, so that's 0, negative 2, negative 4 and positive 3. Adding that to our third row, 0, 2, 4, negative 3, and when we add those together we have 0, 0, 0 and 0. Interesting. We have a full 0 row. Notice now this is actually in reduced row echelon form. Okay, and we can read off our solution. But let's write down what we have. X, 1x plus 0y plus 3z equals negative 1/2. Alright, I'll just write that down. We won't worry about the 0y, so it's just x plus 3z equals negative 1/2. 0x, we won't worry about that. Y plus 2z equals negative 3 over 2. And here we have nothing. There's nothing more we can write. Now this is okay. Well, I suppose essentially we could just write z equals z from that. A little bit confusing. When you've got a 0 row like that, I'll explain what that means graphically in a minute. But what we do typically, now this is okay to write it like that, but another way to write it is what's over here, okay, in what we call parametric form. What we do is we let z take on some arbitrary variable, say t. So if we have z equal to t, then we have x plus, we have in place of our z a t, so it's x plus 3t equals negative 1/2. And then if we were to rearrange that so that we can express it, have an expression for x, x equals negative 3t minus 1/2. okay, or we can put it in as a single fraction, which is shown over here. That's equivalent to negative 16 minus 1 all over 2. Our next one here, from this equation, y plus 2t equals negative 3 over 2. And so solving for y, we have y equals negative 2t minus 3 over 2. Putting that into a single fraction, we'll have negative... there's an error there. I've just spotted that. Okay, it should actually be y equals negative 4t minus 3 over 2. I'll have to change that. Okay, you might want to just put a little correction on that. Okay, so then these are our solutions. We don't actually have numerical solutions for this, except that z can take on any value we like. If z is equal to, say, 0, then we will obtain particular numerical values for x. It'll be x equals negative a half and y equals negative 3 over 2. If z was equal to 1, then it would be different again. It's negative 3 times 1 minus a half. Okay, and so on. Alright, what does it mean though graphically? Let's get a picture of it. Okay. By the way, this is what we call parametric form, our solution that we have here. Okay, just taking note of what's written here. The zeros in the third row do not indicate there is an error. What it means graphically is that there is no unique solution. Now, we know that when we have linear equations in x and y, that represents a linear graph, a straight line, okay, in 2 dimensions. We have 3 unknowns, okay, so what that means graphically is that not a straight line, a line as such, but a plane. Like you're going to picture it in 3 dimensions, okay, it's a plane. And when we have simultaneous equations in 3 unknowns, we have effectively intersecting planes rather than intersecting lines or curves. Alright? So an intersecting planes. And what that means in this case, when there's no unique solution, is that the planes which each of the equations represent don't intersect at one unique point in the x, y, z coordinate system. They intersect on a line, so that really there's an infinite number of solutions. So if we have a look at the figure below, alright, this actually is a graphical representation of these 3 planes that we've worked through. Notice here we've got a plane here, the grey one, we've got a blue plane and a red plane, and they all intersect along a common line. Okay, so that's really interesting. Okay, so that's where we say that z might take on a particular number, and so which will correspond to a value of z in the coordinate system, and then we can find our corresponding value for x and y along that line. Okay, I hope that makes sense. Okay, note here, if the third equation was changed to x plus y plus z equals 1, okay, then the 3 planes would intersect at a unique point, and we would get specific values for x, y, and z. Okay, it might be worthwhile just trying that out. Alright, so hopefully you've got a picture of how to work through this algorithm, and you'll be able to work through some of these problems. Okay, try these problems here. These are just with 2 unknowns, and then we've got 3 unknowns here. Okay, when it says using matrix methods, it means the same thing, okay, as Gauss-Jordan algorithm. Alright, have fun with that.